So question number 3. The question number 3 says, for the following function, find the critical point and classify using them the second derivative test. So we have to use the second derivative test here. So first write down the function. My function is f, x, y, and, okay, there is f, x, y only, no z. So 2x, y, minus x square minus 2y square plus 3x plus 4. So this is my function. The very first thing I need to do is I need to find the critical values, because critical values are where the maximum local max or local min can exist. So to find the critical value, first step is step number 1. Critical value. So what we do to find the critical value, we take the gradient of the function and we set that is equal to 0. This is what you do. You compute the gradient of your function, of the function which is given, and then you set this thing is equal to 0. So what is the gradient? The gradient is the partial derivative of the function with respect to x, comma, partial derivative of the function with respect to y. We're going to compute the partial derivative with respect to x. We're going to set that term is equal to 0. Then we're going to compute the partial derivative with respect to y, and we're going to set that is equal to 0. So what is the partial derivative with respect to x? So it's going to be 2y minus 2x plus 3 is equal to 0. Is that clear? The partial derivative with respect to s, treating y as a constant. And then partial derivative with respect to y is going to be 2x minus 4y is equal to 0. 3x plus 4, they are constant, they will go to 0. Now, the goal is basically to solve these two equations. There are two unknowns and there are two equations. They are solvable. They may have a solutions, and we want to find that solution. The method I use is, the method of back substitution. I'm going to find x from here and plug back into the first one. So what is my x? My x is going to be 2y. If I move 4y on the other side and divide by 2, my x is going to be 2y. And if I plug that x is equal to 2y back into the first equation, let's see what I get. So 2y minus 2 times 2y plus 3 is equal to 0. This is a 2y, I replace x by 2y. If you add them up, this is going to be a 4, this is going to be a 2, this is going to be a negative 2y plus 3 is equal to 0. Therefore, y is nothing but this is equal to 3/2. There you go. So if y is a 3/2, and what is my x? Remember, my x was 2y, and y is a 3/2. So 2 times 3/2 is 3. So I get a critical value. So the point x is a 3 and y is a 3/2 is a critical value. Is a critical value. So I find one critical value. So I think the function has only one critical value. Sometimes it will have more than one critical value. Depending on when you plug back x into the previous equation, if you get the quadratics, you're going to get 2 critical values. Or if you get the cubics, you get 3 critical value, and so on. Okay, once we have the critical value, what we want to do is we want to test this critical value. So step number 2 is we're going to test, whether this critical value, it achieves the maximum or minimum, or it's a saddle, or we can't do anything. So these are really going to depend on this matrix. So test. Second derivative test. There is no first derivative test in the higher dimensions. The reason is because you have, there are so many ways to approach a point. Because if you are in the first dimension, there is only 2 ways, the left and right. So you check the sign on the left, you check the sign on the right, and you say, okay, if left is a positive, right is a negative, positive to negative, let's go. So positive to negative is a maximum, negative to positive is a minimum. But in a three dimension, there are so many ways to approach a point. So you can really never test so many directions. So you have to do the second derivative test. So second derivative test is you compute this Hessian, which is denoted by dxy, which you have to remember. The definition of this is xx f yy minus fxy square. Again, this is a partial derivative of f with respect to x twice. This is a partial derivative of f with respect to y twice minus partial derivative of x then y, the square of this. So let's see what this term is in our function. What is the partial derivative with respect to xx? So this was the partial derivative with respect to f one time. If I differentiate this function one more time with respect to x, what I get? I get negative 2. And if I differentiate the second function with respect to y one more time, what I get? I get negative 4. And if I differentiate the first one, because this was the partial derivative of f with respect to x one time, if I differentiate this with respect to y, it will be partial derivative of f, x, and then y. So this is going to be 2 and 2 square. So this number is 8, I believe, and this number is a 4. 8 minus 4 is a 4, which I believe is a positive number. So there you go. Miss all. Okay, I'll give you a time to think how these partial derivatives comes, So because it's very difficult to fit everything in one sheet. Oh, no, there is a way. Partial derivative of this with respect to xx is a negative 2. Partial derivative of this with respect to yy is, partial derivative with respect to yy is a negative 4. Minus xy is coming from here, which is a 2. If you plug everything is there, it is a 4, and 4 is a positive number. If the number is a positive, it means the function possesses either maximum or minimum. There exists a maximum, there exists a minimum, depending upon if the function has the critical values. This function does have the critical values, so we're going to get something from here. But this will depend on, so therefore, if I plug 3 and 3/2, because there is nothing here, so it's going to be again 4. This is a positive. And what is the value of fxx at 3/2? This is going to decide whether the function has a maximum or minimum. That was a negative 2, which is a negative. If the Hessian, if the d is a positive, the determinant is a positive, it means it exists a maximum or minimum. And if the second derivative is negative, what will be the conclusion? It's a maximum. Saddle point is if this is a negative. If the d is a negative, then it's a saddle. And if d is 0, we are done. Can't say anything. But if fxx is if this is a positive and this is a negative, this will give you the maximum. So maxima is equal to 3 and 3/2. What is a maximum? Yeah, be careful with the language. English is a very tricky language. Maxima and maximum are two different words. Maxima is a point, maximum is a number. So what is a maximum? Maximum is a number when you plug these values into your original function. Yes, there is going to be one question which is going to be similar to number 4. Find the maximum distance from the cone. This is a cone which is a z is equal to the square root of x square plus y square. And so let me try to draw something. I'm very good at drawing. Let's see. Oh my God. Oh, yeah, we're successfully able to draw a cone. And there is a point. So somewhere there is a point in -6, 4, and 0. What we want to do is, we want to find a point on the cone which is the closest to this point, you know. This is what we want to do. This is our problem. So let's suppose you take a point x, y, z. I want to find the coordinate of x, y, z so that this point is very close to the point -6, 4, and 0. This is what we want to do. And how we're going to do is, let's see. First thing, if you want to see what this point is closest to this point, what has to be minimized? The distance. It means distance is shortest distance between these two. And what is the distance between these 2 points? The distance between these 2 points is x plus 6 square, distance formula, y minus 4 square plus z square. This is the distance. The distance between 2 points. How to do that? The distance formula, you know, x minus x value plus y minus y value plus z minus z value, the square of all, add them, and then take the square root. I want to minimize this quantity. This is my minimizer. And let's see. So my problem is, I want to minimize this square root thing, but I will not minimize the square root because that is complicated to compute the derivative of square root. I will minimize the inside of this square root because the minimizer of the quantity which is inside is going to be the same as the minimizer of when you take the square root of the problem. You know, so it's going to be the same thing. So I will minimize this function. I'm going to denote it by d x comma y is x plus 6 square y minus 4 square plus z square. I want to minimize this, but I have to have a condition. I can't minimize, otherwise you can take any point and go close to, you know, this point. And the closest point will be -640 if I don't put a condition. So I'm going to minimize subject to this condition. Z square, I put the square on the z, that will be easy. X square plus y square. Okay. What I'm saying is, I want to find the minimum distance, but my point should stay on the cone. If it go off the cone, then I know my minimizer is the obvious point, -6, 4, and 0. You know, so that's my goal is, I want to stay on the cone and same time I want to minimize the distance. So that is called the minimizing problem, optimizing. Okay, let's see how we're going to do. So there are 2 ways to do it. One is the difficult and one is the easiest. And the difficult one is, what do? You compute the z from here and plug back into the first one, and then you have a problem, which is like a 2-dimensional. And then you compute it. You know, that's the one way. You compute the z from here. It's not even difficult to compute the z. You plug it here, and then you get the function in x and y. You compute it that way. But there is another guy, his name is Lagrange. He invented the Lagrange conditions, which are going to make this problem a lot easier than the one I told you before. So let's see. So the Lagrange, how to spell Lagrange? L-A-G-R-A-N-G. Lagrange multiplier. What are the Lagrange multiplier is? So this function, I'm going to take this function as a z, x comma y. I'm going to get now the relation, which is going to be z square minus x square minus y square. Okay? So Lagrangian said the gradient of my d is equal to the scalar multiple of the gradient of my g. The gradient of the function when I want to minimize, if this is equal to lambda time the gradient of g, that equations will give you the critical values. And these critical values will have maxima or minima. You know, because this problem is a very real life, you don't have to check whether it's a maxima or a minima, it will give you one. So this is the Lagrangians, see, from Europe. Okay, let's see if we can do it. So the gradient of d means the partial derivative of this with respect to x, with respect to y, and with respect to z. So we have to compute the partial derivative 3 times, first with respect to x, then with respect to y, and then with respect to z. And this is called a gradient if you put that in a vector. What is the partial derivative with respect to x? It's going to be 2x plus 12. You move the 2, it's going to be 2x plus 6. You move 2 inside, it's going to be 2x plus 12. That is equal to lambda time the partial derivative of z with respect to z. They're very close word actually. With respect to x, it's going to be a minus 2x. Is that right? The second question is, you take the partial derivative of this with respect to y, is going to be a 2y minus 8, and this is lambda time partial derivative with respect to y, is going to be a 2y, and now the with respect to z is going to be 2z, that's the easy equation, and this is a lambda time partial derivative with respect to z is, did I make a, oh, there is no square here, oh, yeah. Okay, there is no square on the z. Yeah. No, actually, no, right. Yeah, there is a square root. Find it out. Yeah. I took my word back. Okay. And this is going to be 2z. Okay. I was thinking I'm gonna solve the problem, but okay, still we are on the right track. It's not that. Yeah, sometimes you make a mistake and you make the problem easy, and sometimes you make a mistake and you make the problem difficult. This time I wasn't going to make it easier. Okay, so there is a one condition, this is a one, question number 2, this is a question number 3, and there is one more question which is basically this, z square is equal to x square plus y square, so this is a question number 4. So now, what is the situation? We have 4 unknowns, x, y, z, and lambda. And we have 4 questions, 1, 2, 3, 4. 4 questions, 4 unknowns, mathematically the system is solvable. We can solve the system, it's not indeterminate, it's a determinant. But the question is how? How are we going to solve this? There is a 4x4 system. So sometimes there is a systematically way to solve it. Which one I do is basically I separate lambda from each of one, and then I equate one by one. So the way I do is I always in class basically do a very systematically process. It takes same amount of time when you do the systematical process, but sometimes there is a shortcut. Shortcut is a means sometimes one question give you immediately the solution. Some question become very easier to solve and give you the immediate solution. In this equation, in this system, look at the 3. Equation number 3 implies 2z minus lambda time 2z is equal to 0. I move on the other side. I can pull out the 2z and I get 1 minus lambda is equal to 0. And here what I get, z is equal to 0 or lambda is equal to 1. I get my z is equal to 0 from question number 3 and lambda is equal to 1. So I immediately find some values of z and lambda from question number 3. Rather than I systematically solving first like I divide by 2x on other side and then divide by 2y and 2z and then set them is equal to 0 and do all these things. But I have the solution from question number 3. If my z is 0, what that means? Question number 4 implies x square plus y square is also 0. The square of two number is 0, it means x is equal to y is equal to 0. Therefore, 0, 0, 0 is a point, is a critical point. Okay, this is a critical value or the critical point which will be considered. Okay, I'm running out of the space, so let's see. If lambda is equal to 1, what is going to happen if lambda is equal to 1? Question number 1 implies, if I plug that lambda is equal to 1 in question number 1, what I get 2x plus 12 is equal to minus 2x, which gives me x is equal to 12 divided by 4 is 3. Okay. If I plug my lambda is equal to 1 in the very first question, I get x is equal to 3. If I plug into the second question, what I get? I get again 4y is equal to 8, y is equal to 2. Anyone? Negative 3, yes. That's good, very good. And this is a positive 2, okay? So this point, therefore, what is the x and y and what is the z now? Let's see what is z. So x is negative 3, y is 2. If I plug negative 3 and 2 here, what is my z then? You know, or even the very first one. So 3 square is 9 and 2 square is a 4. What is a 9 plus 4? Is a 13, so it's going to be a square root of 13. Is another critical point. Okay, so these are the two critical points, the 0, 0, 0, negative 3, 2 and square root of 3, you know, by solving this 4 by 4 system. Okay, the last things we have to verify is this. Which one is the minimum? Which one will give you the minimum distance? So let's plug this one, d 0, 0, 0, and then d negative 3, 2 square root of 13. If I plug 0, 0 here, 6 square is a 36, 36 plus 4 square is a 16, 36 plus 16 is what? 52, 52 plus 0, 52. Okay, this is a 52. Let's see what happened. This is 3. So 3 square is a 9. 9 plus 2 square is 4. 9 plus 4 is a 13. 13 plus 13 is 26. And who's going to tell me which number is the largest and which is the smallest? Yeah, to my belief, I think this 26 is the smallest number according to many mathematicians. So this point is the minimum point. This point gives you the minimum, and the minimum distance is, therefore, the minimum distance is the square root of 26. Do not forget to put the square root, because I find the minimum of this function. You know, I find the minimum of the function which is underneath, inside the square root. So the minimum distance is going to be 26 square root, because that's the minimum. Okay, this problem is important for your exam perspective. But the process is the same. So you first find out what you have to minimize and what is your constraint. And then you play the Lagrange multiplier. You're going to get 4 equations. You have to solve these 4 equations. You can solve by systematically. The systematically is you find the one variable from the first equation, plug into the second one, find the another one from the third one, and substitute in the fourth one. And you play with them until you get all the critical values. So once you have the critical values, you plug back into your function which you're supposed to minimize or maximize. And the smallest number is the minimum, the largest number is the maximum. Okay, so let's see, find the absolute maximum. Yeah, let's do this one, number 5 too, because then I will do 5 and 6 and let the Brennan to do the double integral integral. Number 5. Oh, what is saying number 5? So find the absolute extrema, means maxima or minima, of this function. Isn't that the same function? X square minus xy plus y square minus 1. on the triangular plate in the first quadrant bounded by these lines. So let's try to draw a diagram. They say y is equal to x, this is a y is equal to x line, y is equal to 4, this is a y is equal to 4, x is equal to 0, this is x is equal to 0 line. So this is a y is equal to x line, and this is a y is equal to 4 line. So what the problem is to find the minimum subject to this condition. So you have to find the maxima or minima or the absolute maximum minima, but it has to be in this domain. Yes? Which one is a -1? Oh, it's a +1? Okay. Here you go. Okay, thank you very much. Okay, what we first have to do is, first we have to find the critical value. And there is going to be a lot of critical values here. The critical values which are inside the triangle, and the critical value which is on the boundary of the triangle. So you have to find them separately. The critical value, so there is going to be two types of critical values. Step number 1 is the critical value. Find the critical value. So one type of critical value is going to come from this, which is called a gradient. If you set the gradient is equal to 0, you will get some critical value. And you're going to keep those critical values which are on or in that interval. Because we are only interested in finding the maxima or minima inside or on the boundary of this triangle. So let's do that very quickly. So partial derivative with respect to x is a 2x. Minus y is equal to 0, partial derivative with respect to y is minus x plus 2y is equal to 0. So if I solve this for x, this is x is equal to 2y. This is a one equation, and I plug that equation back into the first one. What I get? I get 2y minus y is equal to 0, and therefore y is equal to 0. If I plug that, since x is equal to 2y, therefore this is equal to 0. Therefore, I'm going out of the paper or not. 0, 0 is a critical value. So I find a critical value which is a 0, 0, which is on the boundary of this interval. So this is a one critical value. Okay? So one critical value is coming from when I set the gradient is equal to 0. Sometimes you get more, but if you are lucky tomorrow, you get 1. You know? Hopefully, hopefully. Don't trust Brennan because he'll never give you one critical value. Okay, so one critical value is coming from here. So you have to do is, now there are three boundaries. X is equal to y, x is equal to 0, and y is equal to 4. We have to find all the critical value which lies on these boundaries. And corner are always the critical value. The corner of the domain, they always become the critical value because these are the end point of the domain. Okay. So let's see what is going to happen when y is equal to x. I want to find all the critical value on this line. I want to find the critical value y is equal to 4. And I also want to find the critical value when x is equal to 0. So I have to solve three different problems, of math 125. You will see that it's going to become math 125. My function is this. If I plug y is equal to x, it's going to be x times x, which is x square minus x square plus x square plus 1. What I did, x is equal to y, I plug y is equal to x in my very first equation of the function. If you simplify, you get x square plus 1 fxx. And if you take the derivative of this function, you get 2x plus 1, 2x plus 0, so derivative of 1 is 0. And if you set this is equal to 0, you get x is equal to 0. Okay. So therefore, if x is a 0, if you plug x is equal to 0 here, your y is a 0, is another critical value. It's not another because it's the same, is a critical value. I get the critical value, but it's redundant, it's a repeated critical value. If I plug y is equal to 4 in my function, so now x and y is a 4, what I get? X square, and this is a 4x. 4 square is a 16, 16 plus 1 is a 17. Okay. For the critical value, what I need to do is, I need to take the derivative. This is going to be 2x minus 4, and then you're going to set is equal to 0 for critical value. I take the derivative with respect to x, because this function is only in x, and I set this thing is equal to 0. And if you remember math 02 or math 101, this number is 4 divided by 2. This is how we teach, and this is a 2. You take the 4 on this side, and then you divide it by 2, and that you get 2. That's the most difficult part of the math, This is the beauty of the math, how you get 2. So if x is a 2, what is a y? If you plug here, y is a 4, so this is another critical value. Critical value. Okay, so now x is equal to 0, this one. Hope everything becomes 0. X is 0, then y is this. And this becomes y square plus 1. X is equal to 0, this becomes this. If you take the derivative for critical value, we have to take the derivative for critical value. This is a 2y plus 0 is equal to 0. This implies y is equal to 0. X is already 0, y is also 0, is a critical value. Okay, so let me put these critical value here. How many critical value? Let me first write down here actually. How many critical values we have? I think we can do the problem here. So 0, 0 is a critical value which is coming from the gradient, and then 0, 0 repeat it again. Then you have 2, 4. So x is a 2, y is a 4 somewhere here. This is a critical value. And then 0, 0 is again a critical value. So this is a critical value, this is a critical value, this is a critical value. So these are the 4 critical value, 1, 2, 3, 4. So there are 4 critical value. As I told you, the corner are going to be critical value no matter what. Corner is always going to be the critical value without doing anything. So these critical value you get for free. So do not miss them, because you're going to lose the point of you miss the one critical value. 1 point for each. And you don't gain anything if you put it there. But you lose. Okay, let me see. Ladies and gentlemen, so there were 4 critical value. F evaluated at 0, 0. F evaluated at 2, 4. And I need a help. And then what is a 0, 4? And what is the other one? 4, 4? This is a labor work in math. Who gonna tell me what is if you plug F 0, 0 in my F? If you plug 0, 0 in my F, you get 1. If you plug 2, 4, please quick, hurry up. 1 extra credit. 13. So somebody said 13, 1, 3. Lucky number 13. 0, 4. 17, 1, 7. Okay, Zalma, hurry up. 17 again? 1, 7 or 7, 0? 1, 7. No, there is an issue now. So, what do we want to do actually? Problem. A problem is asking find the absolute max and absolute min. So clearly, this number is the smallest. So this is a minima. So minima here is 0, 0. You know. These two numbers are the largest, but they tie. So they have two maxima. So the maxima are basically 0, 4 and 4, 4. So there is a tie between two. So this is the maximum value, but these are the maxima. Absolute, they called it also absolute. Any questions? Ladies and gentlemen. Yes. Where I get 0. So you said, yeah, here and here. So corners are going to be the critical value no matter what. They are free critical values because these are the end point of the domain. So whenever you see the corner, so compute that. Maybe you are lucky. The maximum is, if the maximum occur at the corner and you get the right answer, maybe grader miss the calculation. You know. Yes, you will not be lucky if the boundary is a circle. You know. Yeah, circle does not have any corner, so no critical value. Okay, we have 9 minutes and I'm going to do one question which is important, which is very, very important, and this is my hint. 6. A cardboard without a lid, you know, this lid, with the lid or without a lid is very important, okay? If you have a lid or if you don't have a lid. Let me draw a box. This is the only picture in math I can draw correctly. So this is a box, but this does not have a lid on it. So if this is a X, this is a Y, this is a Z. So what do you say? Say again, read the problem. A cardboard box without a lid is to have a volume. Volume is 32. So what that means is, if I multiply X, Y, Z, it has to be 32. Okay? And what we want to maximize or minimize the amount of cardboard, find the dimension that minimize the amount of cardboard used. So the amount of cardboard is what? It is the surface area of the box. So we want to minimize the surface area. So minimize this surface area S, which is a function of X, Y, and Z, which is going to be XY. So the surface area of the bottom, but there is a no top, so XY is going to be this, plus 2 times of YZ. The surface area of this side, but there are 2 of them. This side is equal to that side. And then 2XZ, I guess, because the front and behind the back, they are also same surface area. So your problem is to minimize this function subject to that condition. You know, to minimize this subject means the constraint is G, X, Y, Z is equal to X, Y, Z minus 32. That problem was in your practice exam. The only thing is differ 32,000 to become 32. Okay, yes.
Can you explain one more time the equation?
Yes. How I get the equation? The very first equation I got because they told me the volume has to be 32. The volume of the box. What is the volume of the box? If the dimension is X, Y, and Z, X times Y times Z, it has to be 32. So since this is an equation, that has to be my constraint. The equation is always a constraint, you know. But they want to find the minimum surface area. They want to find the minimum cardboard. It means that is the surface area of the box. It means that is one I'm going to minimize. So this is going to be my main function, and this is going to be my constraint, because that is the equation. Again, there are two different ways. One is the difficult one is the easiest one. The difficult one is you find z from here, plug back into the first equation, and do all these calculations, and if you are lucky, you will get the answer. Any question before we move to the calculation part? How you get this question? Yeah, this is the surface area of the box. The surface area is the surface area of this, which is a xy, and surface area of this is a yz, but there are two of them, so I put 2 here. And the surface area of the front, which is a xz, but there are two of them, front and back. So this is I get the second equation. Okay, so let's see the Lagrange multiplier. Lagrange multiplier. What is the Lagrange multiplier? It says the gradient of S is scalar multiple of the gradient of G. This gives you the critical value of your function. The gradient of S is equal to lambda times the gradient of G. So let's do it quickly because Dr. Brennan is here. The partial derivative, so we're going to compute the gradient. What does it mean gradient? The partial derivative with respect to x, y, and z. And you're going to put all these in a vector. That is equal to lambda times partial derivative of x, y, and z. You put everything in a vector bracket. If you set these two things is equal, what do you get? The very first equation you get, the partial derivative with respect to x of this equation, which is a y plus 2z is equal to lambda times partial derivative with respect to x of this equation, which is going to be yz. Okay, this is our first equation. The second equation is a partial derivative with respect to y is going to be x plus 2z is equal to lambda times. This is going to be now with respect to y is going to be a yz. Okay. So this is with respect to y. So this is going to be xz, and this is going to be, this is going to be yz. Okay, so the last one is partial derivative with respect to z. This is going to be 2y plus 2x, and lambda times the partial derivative with respect to z is xy. And then you have one equation x, y, z is equal to 32. So this is equation number 1, this is equation number 2, this is equation number 3, this is equation number 4. So you have 4 unknowns, x, y, z, and lambda, and you have 4 equations. So system may give you a solution if it is a consistent. And most of the time when these practical problems, system is consistent. They give you one solution or 1 or 2. How to solve them? That's the most important thing. There is a way of systematically solution, or there is a way you can just find it a way. Basically, you can trick yourself. One way is you move that y and z, because y, z are dimension. They are always going to be positive. You can move this on this side. You can move this on this side. You can move this on this side. You have lambda on this side. So you can set 1 is equal to 2 and 2 is equal to 3, and you get some relation. And then you plug all these relations into the fourth one, and you get the values of your x, y, and z. Let's see if we can do. Okay, what I'm going to do is, the very first equation, if I multiply this equations by x, I have lambda x, y, z. If I multiply this equation by y, I have a lambda y, z. If I multiply this equation by z, these sides are equal. Instead of dividing, I'm going to multiply by x, y, and z to the first 3 equations. So in the very first one, I'm going to get x, y plus 2xz is equal to, if I set this is equal to the second one, is going to be a xy plus 2yz. This I can cancel out because the dimensions are always positive. So therefore 2xz is equal to 2yz Z cancel out. Therefore, 2x is equal to 2y. Okay, x is equal to y. So the x is equal to y. If you do this same thing, this is a 1 and 2. Now you do 2 and 3. Let's see what you get. So 2 and 3 is, if you multiply x, y plus 2y, z, this is going to be, I'm going to multiply the third equation by z. This is your 2z y plus 2xz, which cancel out. 2yg, this one. You have xy is equal to 2xz. X cancel out, so y is equal to 2z. Okay? Now I have two relation. I have x is equal to y and y is equal to 2z. This implies this is also 2x. No. This implies z is equal to 1/2 y, but y is equal to x. It's a 1/2 x. So I have the value of y in term of x, and I also have the value of z in term of x. Now I can use the equation number 4. So if I use number 4, what I have? X, y is a x, but z is 1/2 x. This is equal to 32. So the x cube is going to be 32 times 2, which is a 64. X is 64 to the power 1/3. What is the 64 to the power 1/3? 4. So this is a 4. So if x is a 4, what is a y? 4. And what is a z? 2. So your dimension is, so this is a x is equal to 4, y is equal to 4, and z is equal to 2. This is your dimension.